Hi, my name is Mohammed Bakr Sikal, a PhD student at the Khdr Institute of Technology in Germany, and today I will be presenting to you our recent research paper entitled Machine Learning-Based Thermally Safe Cache Contention Mitigation in Clustered Manycores. Performance maximization on many-core processors has been bottlenecked by the processor memory cap for decades. And one way to solve this problem was the introduction of more advanced multi-level memory hierarchies which comprise multi-level caches. For example, the modern AMD Zen 3 clustered many-cores have multiple cores in each cluster, and cores within the cluster share the same last-level cache. However, executing multiple applications simultaneously on many-cores can degrade their performance for two reasons. First, concurrently running applications on one cluster compete for the limited available cache. Such cache contention slows down the application execution, thereby degrading the overall system performance. The second type of interference between concurrently running applications is the heat transfer between their cores, which might occur even across clusters. If temperature increases beyond safe thresholds, the thermal control circuitry, which typically exists on commercial processors, is triggered to cool down the chip by setting the voltage and frequency level of all cores to the minimum, irrespective of the core causing the violation. Both these types of interference eventually result in execution slowdown, and this can be seen in modern clustered many-core platforms, as we will demonstrate in the next motivational example. Here, we run simulations on a clustered many-core processor with 3 clusters using applications from the Splash2 benchmark suite. Initially, 2 applications, LU-Cont and X264, are co-running on cluster 1. WaterSP is running alone on cluster 2, and Barnes is running alone on cluster 3. Compared to its alone isolated execution time, we notice that LU-Cont is suffering a slowdown of 23% due to cache contention with X264 on cluster 1. This slowdown could be potentially avoided if we migrate LU-Cont to cluster 2 or to cluster 3, but which option should we select? We run experiments to find out the implications of each possible migration. When we migrate LU-Cont to cluster 2, we notice that WaterSP is barely impacted, while LU-Cont achieves a boost in its performance by 16%. While this is a significant performance improvement, we also notice that the system temperature reaches 83.5 degrees Celsius. Assuming a temperature constraint of 80 degrees on the system, this is a temperature violation. When we migrate LU-Cont to cluster 3, we notice that Barnes is barely impacted, while LU-Cont achieves an increase of 8% in its performance. While the performance improvement is less than the previous migration, the overall system temperature does not exceed the temperature threshold of 80 degrees Celsius this time. Now, which option should we select? Option 1, with the minimum contention, the best performance increase, but thermally unsafe, or Option 2, with the medium contention, relatively good performance improvement, and thermally safe. Here, we can clearly see a trade-off between cache contention and temperature that needs to be considered in clustered many-cores. However, selecting the best migration option depends on the knowledge of the performance and the temperature numbers, as we have seen in this example. At runtime, before performing the migration, these numbers are unknown and should therefore be predicted. While temperature prediction is well studied in the literature with the well-known RC thermal models, predicting the impact of cache contention is much more complex, as we will see in the next couple of slides. First, to gain more insights about the complexity of the problem at hand, this table shows the slowdown experienced by application A due to application B, both from the Splash2 benchmark suite. The first observation is, while Stream Cluster is not slowed down by any application in these experiments, it has slowed down all applications it was co-mapped with on the same cluster. Secondly, different application pairs have shown different slowdown behaviors. LU-Cont, for example, suffers a slowdown of 20.8% from Stream Cluster and 27.2% from Kolsky. You might conclude that Kolsky will always cause more slowdown to an application than Stream Cluster. Well, that's not exactly true. If we look at LU-Cont this time, when co-mapped with the same two applications, we can see the opposite trend. This time, LU-NCont suffers a slowdown of 22% from stream cluster, but only about 17% from Kolsky. These different behaviors show already that slowdown prediction will be a complex problem. So we tried to find possible predictors or indicators of this slowdown behavior by looking at LLC and DRAM accesses of a couple of applications. If you remember from the previous motivational example, X264 had caused LU-Cont a significant slowdown of 23%. Looking at its performance counters, X264 has indeed showed a high number of LLC and DRAM accesses compared to other applications. If you remember also, when we tried the two migration options, LU-Cont had suffered more from Barnes on cluster 3 than from Water SP on cluster 2. Following the same logic, one could think that Barnes would show higher numbers of LLC and DRAM accesses than Water SP. Well, the simulation results showed the opposite trend, as Water SP experiences higher LLC and DRAM accesses than Barnes. With this counterintuitive observation, we wanted to further investigate and understand the slowdown behavior of applications. In this plot, for instance, we can look at the number of LLC accesses and misses performed throughout the execution time of Canil, an application from the Parsec benchmark suite. And we can clearly see the significant change in the application behavior as it changes phases throughout its execution. The slowdown behavior on a cluster where this application would be running will be very different depending on which of these phases the application is currently in. So at runtime, many applications will be running on the same cluster, each with their own characteristics and phase changes. And with such an exponential growth of the number of possible combinations, even design time profiling of applications becomes infeasible. To tackle this complexity, as we will see next, we employ a neural network model to predict the execution slowdown of applications before performing a migration. To this end, we propose SmartCM, the first task migration technique that jointly mitigates cache contention and enforces thermal safety in clustered Manycore systems. It is enabled by a lightweight and accurate neural network, which is used to predict the impact of a migration on performance, considering cache contention on source and destination clusters. To build SmartCM, we start by running multiple simulations on the Hot Sniper simulator with all combinations of two benchmark applications from Parsec and Splash2 at all supported frequencies with the large input size. Having all the possible combinations makes it possible to emulate application migration scenarios where initially an application of interest, AOI, is running with an application gamma, then migrated to another cluster to co-run with another application omega. Iteratively, we then compare the slowdown behavior of the applications through a fine granularity analysis by looking at 10 millisecond long slices from their simulation traces. From each execution slice, we extract all the recorded performance counters of each application and the resulting IPS of the application of interest as a proxy metric of performance during that 10 millisecond slice. We then run a feature important analysis and shortlist the following set of features per cluster. Data of each slice is one row in the training dataset, and this process is repeated to cover all the execution traces of all possible combinations. Data of each slice represents one row in the training dataset, and this process is repeated to cover all the execution traces of all possible combinations. This dataset is used to train a lightweight neural network with 4 layers, which achieves a mean absolute percentage error of only 2.3% and an inference time of only 13 microseconds on our target platform. At runtime, we periodically search for possible migration candidates, meaning applications that are not running alone on a cluster but have other possible destination clusters where they could be migrated. SmartCM then invokes the neural network to predict the IPS on source and destination clusters, and if a migration is found to improve the overall system performance, we check its thermal safety using our RC thermal model of the chip. At this stage, only thermally safe migrations that resulted in performance improvements are kept. From this list, SmartCM selects the migration with the highest performance improvement and executes it. Every 1 millisecond, SmartCM also tries to boost clusters to the maximum thermally safe VF level or throttles down a cluster when a potential temperature violation is predicted. To evaluate our technique, we run experiments on a simulated 64-core clustered processor with 8 clusters of 8 cores each, and cores within a cluster share 8 megabytes of last-level cache. We compared SmartCM against a state-of-the-art application migration technique that mitigates cache contention under a power constraint, which we augmented using thermal safe power, TSP, to enable a fair comparison. The temperature constraint in these experiments is set to 80 degrees Celsius. We used 3 experimentation workloads, each comprising 15 randomly selected multi-threaded applications from Parsec and Splash2 benchmarks. In these experiments, these applications can run at different parallelism levels and arrive at 5 possible arrival rates to the system to simulate different system utilizations. The results of the experiments showed that SmartCM can significantly reduce the cache contention in clusters and result in shorter execution times of applications. Compared to the state-of-the-art, SmartCM achieved up to 45% performance improvements for some applications, which is mainly thanks to the accurate predictions of our neural network. However, we can see on the bottom figure here that some applications have instead shown performance degradation compared to the state-of-the-art, and there are 2 reasons for that. First, the state-of-the-art technique has selected different migration options, which can indeed further improve the performance of individual applications, but that does not necessarily mean that the overall system performance will also be improved. Secondly, a migration by definition will reduce the contention on the source cluster, but would naturally increase it on the destination cluster if there are other applications running on that cluster. Still, looking at the overall system performance, SmartCM has managed to balance the cache contention across clusters and maintained an average performance improvement of 11% in all 3 workloads at all arrival rates. In terms of temperature, SmartCM was able to achieve these performance improvements while also being thermally safe. The state-of-the-art technique, on the other hand, has showed many temperature violations. This can be explained by the fact that the state-of-the-art technique directly applied the decisions of their neural network, which can sometimes be inaccurate. These prediction inaccuracies are automatically reflected in temperature overshoots. SmartCM, on the other hand, only uses the neural network to predict the performance impact, but then still verifies the thermal safety using the accurate thermal model of the chip. Moreover, the cluster-level DVFS will further enforce the thermal safety by periodically adapting the VF level of the clusters. With such a strategy, even in the worst-case scenario, where a migration is performed without resulting in any performance improvement at all, still, it would not result in a temperature violation. To sum up, we have presented SmartCM, the first technique to address cache contention under thermal constraints in clustered Manycores using neural network-based application migration jointly with cluster-level DVFS. With an overhead of barely 1.7% of the migration epoch and only 1% of the DVFS epoch, SmartCM has improved the performance of applications by up to 45% and by 11% on average, while enforcing the thermal safety on the chip. Thank you for watching this presentation video. Check out our paper to know more, or approach us directly if you are interested in our work.